Today we are going to learn how the compiler translates if statements and loops. Okay? And so the assignment, like I mentioned before, the assignment that was normally due today, extra 24 hours so you can have time to do that. But what we learned yesterday, or the last time, was we learned how local variables are stored and how they're stored on the runtime stack and how we use stack relative addressing to access them, how we use sub-SP to push and stack relative address to access and add SP to pop. And now one of the other programs that you were supposed to do for today had an if statement in it, so we're going to learn how those work. Now, and so here on the first slide we have a list of what are called the conditional branching instructions. Okay? And there are, so in order they are branch on less than or equal to, so that's BRLE, and then branch if less than, BRLT, branch if equal to, BREQ, branch if not equal to, BRNE, and branch if greater than or equal to, BRGE, and branch if greater than, BRGT. So those are the mnemonics, and these are called conditional branch instructions as opposed to the branch instruction that we already know about, which is the unconditional branch instruction, which is just plain BR. All right, so you know when we branch to main, that always branches. But these are conditional. So maybe you will, if you execute one of these instructions, maybe you will do the branch and maybe you won't. See, and so these are the instructions, these are the assembly language instructions that we need in order to implement an if statement. Because in an if statement, what do? Your program comes along and it checks a condition. And if it's true, it executes it. If it's not, it doesn't. So the question is, how does the compiler translate the if statement? Well, it uses we need what are called conditional branch instructions at the assembly level. So those first 6 that we just enumerated are all the possibilities for comparing quantities. Less than or equal to, less than, equal to, not equal to, greater than or equal to, greater than. And then there's two other ones, BRV, which is branch on V, and BRC, which is branch on C. So V, now what was the V bit used for? Overflow, interpreting as a what? As a signed integer. And C was overflow interpreting as a what? Unsigned. Well, no, C is set if there's a carry out from the most significant bit, and you're not considering it to be the signed bit. I mean, it's just the carry out. You remember how to do that, right? Those computations. Okay? So now, this is how these branch conditions work in English. The next slide shows literally how the hardware implements these. Because what it does, the way the hardware implements these is it checks the N bit and the Z bit. Now, what does this mean? This means that in order to use this instruction, there must have been a previous assembly language instruction that did what? That set the N bit and the Z bit accordingly. So anytime you use one of these branching instructions at assembly language, you have to think to yourself, what instruction went before that would set those bits so that then there would be a meaningful test for the conditional branch instruction. Is everybody clear on that? So you can't just do a conditional branch without something before setting the N bit and the Z bit accordingly. So let's just take, I'm not going to go through all of these, but let's just take a look at a few of them. So look at the first one. Branch, BRLE, means branch if what? Less than or equal to. So now, when does it do the branch? What does this, what is that called? The RTL, Register Transfer Language? What does it say? If what? N equals 1, so that means that's the N bit. Now N checks for what? Negative. Or what? Z equals 1. What does that check for? All zeros. So if it's negative or all zeros, then what happens? Program counter gets the operand. Now, do you remember that that's how the branch works? What is the RTL for the unconditional branch? It's just what? This is the unconditional branch. And why does that do the branch? Because the program counter stores what? What does the program always have in it? The address of the what? Next instruction. Right. The next instruction to be executed. So when you change the program counter, that changes the instruction that executes next. So in the hardware, what the logic does, the way the circuit is designed and the CPU, is there's circuitry to check if the N bit is set or the Z bit is set, then it does that. Then it does the operand program counter gets the operand. Yeah, question?
Less than or equal to.
Yeah, that's a good question. We haven't seen how these work in conjunction with what went before.
Okay.
So you'd have to see that in that context. Yeah, so that's just kind of coming up.
Okay.
And the details for how all this works, you can kind of get a flavor of it here, but the literal details for how it works, I mean, you'd have to see what went before and how that set something. But I have found that that's a really good exercise to do, but the way the mnemonics are set up, it's pretty easy to see how the translation works and not go through all those nitty-gritty details. You understand what I'm saying? But it's a good exercise to do it, to see precisely how it works. I challenge you to do that, but we're not going to take the time to go at that level of detail of explanation because we just don't have time. But anyway, so those are the branching instructions. Now here's what we're going to do in figure 6.6. Now what we want to do today is we want to go through a number of programs. We're going to do this. We're going to go around the room. Okay? So, get your antennas up. All right? And we're going to do some translations. And I think you'll see, we're just going to learn as we do the translations. All right? So now let's take a look at figure 6.6. Here's a short little program, int main, int number. Now I have a question for you. Is number global or local? So is it stored in a fixed location in memory, yes or no? No. Where is it stored? On the runtime stack. So the first thing we have to do to remember how to translate this is let's draw a picture of the runtime stack. This is a really simple one. So the runtime stack for the main program will just have one cell on it because there's only one variable. And this is called number. And where will the stack pointer be? Well, the stack pointer will be pointing to that one, right? So here the stack pointer will be here. It would be pointing to this. And so what is the stack relative address of number after we have allocated storage on the runtime stack? 0, right? That it will be 0. Okay. So now with that in mind, who wants to start? What's the very first? Who wants to start? Okay, you get it. Branch domain. All right. So now that means that you're next. Okay, so now we're going to branch domain, and now what about number? Yes. So what do we put here? Number, colon, and what do we do for number? Dot equate what?
0.
Correct. Dot equate 0. Now let's be a little more yeah, question?
Can I ask a hypothetical question?
Sure.
What if it had said, was there be 2 steps?
Oh yeah, that's a good question. Now here's the thing. The question is, what if we had said if the program had said int number gets 5? Okay. Now there are many features of C that we are going to, for simplicity, not cover how that happens, and that's one of them. Okay. So anyway,
But it would require like
there would be a way. Yeah, we would have to have a way to. And actually, what you would do? Well, no. Yeah, there's going to be lots of features that we just don't have, just for sake of time. It'd be beyond the scope of the course, That's the kind of thing you would learn in a compiler construction class, actually. All right, but now one more thing here. we need to be careful about our trace tags. You remember what the trace tag would be here? First of all, is this local or global? So we would say local variable. And what's the trace tag? Do you remember? Yeah. So pound 2D or hashtag 2D. So that means a 2-byte decimal. All right, now next. We are in main, that is correct. Yes, and remember, we have to get the stack pointer from here up to here. So this is going to be sub SP. How much?
1.
Okay. Yeah, hold on. Yeah. First of all, what is the type of number? It's an integer. How many bytes for an integer? 2. So sub SP what? 2. Is everybody clear on that? And what's the addressing mode for that? Yeah, see, if it were S, then what? Then 2, yeah, that's it.
We only use like S for like.
Yeah. Yeah. Okay. Do you understand that we want to literally subtract 2 from the stack pointer? So it'd be I. Yeah, exactly. Because 2 is not an address. 2 is what we want to subtract from the stack pointer, so it's immediate. Yeah, now that's important. Is everybody clear on that? Okay. And now we need to be careful about our trace tags here. Because what are we doing? We're pushing what? Numbers. So now we need a symbol trace tag. So we say push, and what do we put? Hashtag number, so that it can be labeled in the debugger. Is everybody clear on that? Okay. Okay. So now next. Now, okay. So the next one is what? Scanf. Scanf D ampersand number. So what is that? Exactly. So deci what? Number. No. Close. Because. Say it. What's your? Well, tell me what to write here. Tell me what. What are the possibilities are I, D, or S? I, D, or S? S. Stack relative addressing. Because the stack is here, the stack relative address of number is 0, so then that's, so we're putting it on the stack there. We're decimal inputting it into the stack there. It is an entirely different, and remember, it's down there in the F area. Remember we said stack pointer is initialized way down there, and
so it's not even.
It's not up by the program. It's not up before the program. It's actually way down there. So remember the memory map. We look at review the memory map.
It's after like FC.
Yeah, it's down there in FF or FC something. Down there. But it's on the memory map. It's a different location of memory.
So unlike all that kind of.
Well, yeah, but we can see it happening on the debugger because remember we demoed the debugger. It'll show it. Yeah. But it is, if you look at the memory map is really crucial because that shows where everything is. There is a place for everything and everything in its place on the memory map. Okay? So anyway, so yeah, that's all right. Okay, so now if number is less than 0, now this is going to be tricky. I think I'll do this one because we haven't done this before. I'll do this one. What we're going to do is we're going to do load word accumulate. Whoops. LD. Load word accumulator into number. Load word accumulator from number using stack relative addressing. Now here's what this will do. This will take the value of number and it will put it into the accumulator. And if you go back and review what load word accumulator does, it sets the n bit and the z bit. So this is the statement when you actually load it, the n bit and the z bit will be set. And so therefore, we are now ready to do the test of the if statement. Now, is everybody clear on that? If you go back and review the RTL of load word accumulator, you'll see that the n bit and the z bit is set. And so now those n bits and z bits are set, and now we can do the test for if number is less than 0. Actually, yeah, question?
So like if you don't do that.
If you
like,
don't do-
bits of like a some like that.
Yeah, there'll be some random. Yeah, there'd be some random whatever they were set to from previous instruction, and it'd be hard to predict. You couldn't predict what would happen. But this will set the n bit and the z bit. Now, I have a question. When do we want to do number gets minus number? Do we want to do that if the test is true, or if the test is false? If it's true. But what instructions do we have to work with? Branch instructions. So the question is, when do we want to branch around if it's false? Do you see? So now, can you tell me, so now here's your question. This is either going to be BR, now it's either going to be BR, now what is less than 0? BR, it'll either be BRLT, or it will be BR, what's the opposite of less than? Greater than or equal to. So now here's my question. So now you can say this if you would like. Do you think it's going to be BRLE or BRGT? Or you can pass. Yeah, that's good.
Wouldn't it be GE?
Sorry, GE. Did I say GT? Yeah, GE. Yeah. So we're going to branch if greater than or equal to. Now, where are we going to branch to? Someplace down there. Yeah, so we're going to have to make up a label. We'll have to have a symbol, you see. So to branch if greater than, and we'll just call it, a convention is to say end if. And that'll be somewhere later. And for a branch instruction, it's optional, so we just leave off yeah.
I'm assuming it would be on somewhere else.
Yeah, now that's a good question. Yeah, that's a good question. Here's what we want to do, and what the compiler will generally do. We want to have the chunks of code be in the assembly language listing where they are in the C program. We don't want to have things mixed up. It's possible to do it that way, but for clarity and for, we want to have the chunks of code be where they are. You see what I'm saying? You could have those way down there, and then you could branch back, and it would be equivalent computation, but we don't want to do that. But that's a good question. That was a good. Okay, so. And if it would be immediate, but we can leave it off. We can leave it off because same way as we leave off branch, the addressing mode for a branch. Oh, by the way, which brings up a little point. Some of you guys didn't read the problem description for your project. We have just a few conditional. Some of these conditional branch instructions are also going to be in your the project. For your translation project. But anyway, now, okay, so now here's what's coming up next. Now, how would you do number gets, now the next thing is an assignment statement. Now, how would you do number gets minus number? What do you have to do? Okay, load word. Okay, so load word what? Accumulator what? Hold on, it's his turn. We got too many. Okay, load word accumulator what?
Oh wait, is number already in me?
That's interesting. Okay, I'll tell you what. Hold that thought. Hold that thought. Let's just do it this way, like your first instinct was. So what would it be?
Number.
So load word, number what? Number, stack relative. And then now next.
Oh, me.
Yeah.
Sorry. Negate.
Yeah, so neg what? Yeah, and that's a unary, right? So this would be negate accumulate. And now what? Now store word accumulator into what? Store word accumulator, number S. And now what? And now, your question?
No, I was just answering.
Oh, okay. But what's the next thing that we have to do? Print. How do we do the printf? Correct. Decimal output. Number is right. Addressing. Number S. And there's one little thing that we have to do with this instruction. Do you remember? You know what else? This is a little incomplete still. Hold on. It's,
Is it not my turn anymore?
Well, it's this instruction. So do you know? Do you know what's missing? There's a little something missing. Yeah, we need the label because this is a branch of greater than to indif, so we need to put indif here. No. You don't output. You never output the accumulator. When you do decimal output, it has to be from memory.
Yeah. And
So you have your choice of those addressing modes. If you want to output what's in the accumulator, you have to move it to somewhere in memory and then output it from the memory. Because deso is a trap instruction that expects to output from memory using one of those addressing modes.
So you can only use that for another location?
Yes. Yes. Yeah, that's a good point because,
You can skip a couple steps.
right, because what you can do, the way you get a single character out with memory mapped I/O is to go from the accumulator to the output port. So this is a little different, isn't it? Yeah. So that was a good point. Yeah. Yeah. We normally do that actually for documentation. So. Where did we do? Yeah, so this is kind of like the start of the if statement. So sometimes we do this. Just put a symbol there, even though it's not used anywhere else in the program, just to document the fact that this is the start of the if statement. Is that what you were going to? Is that what you're asking?
That kind of helps to explain like the second load.
Yeah. That's just for documentation purposes, even though it's not technically necessary for the program to execute correctly. All right, now. And now one more thing. Let's see, whose turn is it? Okay, so now one more thing. We pushed, so since we pushed, what do we have to do? So we have to do add SP to immediate, and now what do we have to say? Pop, and what are we popping? Number. And then stop and dot end. Yeah, question? Yeah, well, it's just pretty clever. Yeah, whenever it's 0. Yeah, now if there was another, the next example, we're going to have a value, and we're going to have a compare, there's going to be a compare instruction. Yeah, but so we'll see how that works. All right, now here, let's see if we did it right. Did we do it right? Somebody check. Are we good? All right, good
Can
deal.
we go back to why we have the double load?
Yeah, now let's go back to that. So look, you guys, here's the thing. We knew that when we did this, load word accumulate, this one. We knew when we did this load word accumulate, we knew because of what we had done before that this is actually, we don't need.
But the computer doesn't necessarily know.
Well, now that's a good question. What does the compiler know? That is a really, really good question. Okay, before I answer that question, here's figure 6.7. Notice that in part A of figure 6.7, this is how it's written in C, and in part B of the figure, this is kind of like what we have to do in assembly language to do this branch around, because we don't have indentation or, like we don't have braces and indentation in assembly language. Are you with me? So this is kind of a little graphic of the difference between HOL6 and assembly language with this branch instruction. Now, so here's the thing. It depends on what you want the compiler to do. Now, what we're talking about now is the concept of an optimizing compiler. Now, what an optimizing compiler will do is it will, quote, remember that when this happens up here, this load word accumulator number, and then a good optimizing compiler can keep track of the fact that that is in there, and then what will it do? It will do what? Just not even generate this. All right? So an optimizing compiler can do that. But now think about, what's the fundamental question of computer science? What can be automated? Now, why did you pause there and say, isn't it already there? Because you knew that what went before would affect how this was executed. But now, do you see that if the compiler only saw number gets minus number by itself, without having to remember any of that stuff, do you see that it would do it just like this, load word, neg, store word, right? Now, tell me, so a non-optimizing compiler would just see that assignment statement and just do these three things. Are you with me? But we can automate this knowledge, we can trace through and figure out what's going to be, an optimizing compiler can keep track of which variables are in which registers in the CPU and eliminate this. Now tell me, if you were writing a compiler, you're writing a translator now, but what if you were writing a compiler? You are writing an assembler, but what if you were writing a compiler? Can you imagine how hard it would be for your program, for your compiler, to keep track of what would be in the accumulator and therefore be able to eliminate this statement? In fact, if you were able to do that and you did run that, tell me, would it take longer or shorter or about the same amount of time for the compiler to do the translation? What if the compiler had to remember all that stuff when it was doing the translation? What do you think about the translation itself? Would it take longer to translate, yes or no? It would. Because there's more logic. It would have to remember all that stuff. More code would have to execute, da-da-da-da-da. Instead of just reading that each step as itself and just boom, doing it, it would have to do all those computations to remember all that stuff. So, the disadvantage of an optimizing compiler is that it takes what? Longer to run, longer to do the compile. But without this extra statement, what about the object code when you run the object code? It runs faster. So if you're running it a lot, you want an optimizing compiler. Now, and here's the thing, you guys. Here's the thing. What happens always in a production environment is compilers have settings. And so it's not you either have an optimizing compiler or you don't. It's you can adjust the settings on the compiler to either optimize or to not optimize. Now, what do you think the engineers do? What do you think the software engineers do who are responsible for maintaining Microsoft Word? Because Microsoft Word is a big program. It's got the huge, it takes hours for it to compile. Now, when those engineers are debugging, are adding a feature to Microsoft Word, what do you think, how do you think they have their compilers run during the day when they're doing what do they want to have happen? They want to put some code in there and do what? Do a real fast what? A real fast compile so that they can test and make another change, compile. So what do you think they have set on their compiler when they're developing and debugging? What do you think? Is optimizing or not optimizing? Not optimizing, because they want to compile fast so they can get the results so they can do some more tests. All right? And then after they get it all debugged, what do you think they do before they release it to the general public? Then they set super optimization, let that compiler run all night long, and then get the Microsoft Word that they're ready to release to the public. Because what does the public want? Microsoft Word to execute fast. Now, does everybody see that? That's crucial. That's a crucial computer systems concept. Difference between an optimizing and a non-optimizing compiler and how you use it. Does everybody see how that works? So that was a really good observation. Wait, it's already there. Yeah. And this is how it all plays out. Are we good? Is everybody good? Okay. Okay, so now the next program, we're not going to compare a number with 0. We're going to compare two different quantities. All right, and to do this, we're going to need the compare word instruction. So this is called CPW, compare word, and there's going to be two flavors, either compare word accumulator or compare word index register. And what it does is it actually does a subtract. It actually subtracts two things, but the only reason it does the subtraction is to set the N, Z, V, and C bits. That's the only purpose of it, is to set the N, Z, V, C bits, so that you can then do a conditional branch afterwards. Okay? And these RTL details are all there, and you can read through that. But we're not going to go through those details. We'll just see how to use it. And now what we'll do is let's take a look at figure 6.8 and do another translation. And but this time, instead of having an if, it's an if-else. Now, who was last? It's okay, so now it's your turn. All right, so, you have it easy. Oh, wait, before we do anything else, is limit a variable, yes or no? No. So is it stored on the runtime stack? No. What about num? It is. So does everybody see, then here we have, here's num. Here's the stack pointer, and okay. Okay, so now you're lucky. Branch to main. Okay, now, next. Yeah, limit, good. Dot equate, exactly. Okay, and next. Num. Dot equate 0 is right, and this is a what? 2-byte decimal, but what is it? We always like to put what it is. It's a local variable, yeah. Right. Local variable, pound 2D. Okay, so next, now where are we? Main, good. Sub SP, yes, sub SP, to addressing, immediate. Yep. Yes, so that will let our debugger, do its thing. Okay, so now scanf D into num.
Yes. So it's
Deci, decimal input.
and then num.
Num addressing mode. S. Is everybody clear on that? Okay. Now here we go. If num is greater than or equal to limit, now is where we use this compare. Now, can you just what do you think?
Like, you have to load num first, right?
Actually, you do, because it compares it with the yes. So what we do is we put the first one in the accumulator. So how do we do that?
Just load word accumulator,
Load word accumulator, num, stack relative addressing, and now we get to use the compare instruction. What are we comparing num with? Limit. So so here, if we go back to this compare word, what do you suppose we do? So compare word accumulator with what? With limit, and limit is, yes, good call. Immediate. Now, question?
Yeah, if you subtract.
Well, yeah, because we're comparing two quantities. So what it does is it subtracts, but it doesn't put but it does not put the difference anywhere. The purpose of it is to subtract, but then it sets the N, Z, V, C bits accordingly, but it doesn't put it anywhere. But it does the same operation as a subtraction.
So you don't have to remove or
Yeah, you don't have stuff. Right, right, okay. So now, it's now, when do we want to branch, yeah, so what's next?
We're gonna branch when that fails, right?
Yeah, so you can read num is greater than or equal to limit, so we want to branch around if num is what?
Less than
Yes, and so it would be BR what?
LT.
LT, excellent. So this is going to be BRLT, and to where? We're going to have to somewhere down. So we'll write a new label down, or a symbol down there named else. All right. And now what do we have to do? Now what is the statement inside the if?
Decimal output.
Yes.
Well, we're not.
Oh wait, word.
Hmm?
Yeah, string output, right.
Oh, sorry, it is a string, right. It's not decimal output, it's string output. Stro, okay, and what do we want to print?
Hi.
Yeah, so that'll be some string down at the bottom of the program. So what do you want to call it? Message 1 maybe, just for, and then what addressing mode?
I.
I think the stros use direct addressing because that message is going to be at a fixed location in memory down there after the program. Isn't it direct? Okay.
Well, because if it was I, it would have been like.
If it was I, it would actually, yeah. Because this message is going to be a symbol, and it's going to be an address.
Hi/id.
Correct, because that's a whole string. You can't put a string in the operand specifier. The operand specifier is only 2 bytes. You can do a single character, but you can't do a string. Oh, yeah, that's a good observation. Is everybody clear on this? Right. But now, how do we get now? Next, we got to do you have to output the bash n. Now this is memory mapped I/O. So what do we have to do here?
Store byte.
Not store.
Load byte.
Okay, so load byte accumulator what? Bash n. Immediate. And now, do you know how to get this to the out? Very good. Store byte accumulator to where? Remember the little symbol that we had? Yeah, good. Care out, and that is what addressing? Remember? It's at it's at a fixed, that output port is at a fixed location in memory. Direct. Okay? And now we're at the else part, right? And so now this was branch if less than to else. So what comes here? So now here comes our else. Oops. Next one. Else. And that's another string output. And that's message 2. Direct. Oh, wait. We just did a major faux pas. Yeah, this was wrong. Yeah, yeah.
Because don't you have to branch around the else?
Yeah. Yeah, now this is an important point. This is incorrect. Why?
Because like if you do all that stuff.
Because if you do all that stuff, how does this statement work in HL6 language? If it's true, you do that, and you what? You skip the else. In assembly language, you got to actually do what? You skip the else. Otherwise, it'll just keep one right after the other.
Would we call that an if?
Yeah. Well, hold on. Okay. Now, so what goes here instead? Yeah, this is an unconditional branch. Are you with me? Because once we get there, we always want to skip around. Is everybody clear on that? To where? Some indent, yeah, to some. End-if. Oh, yeah, that was a major mistake. Okay, now what? Now what? Now else. Stro, message to direct is correct. Message to direct. Yeah, haha, we're getting good at this, huh? And now what?
Dot stop.
No, because we're the printf.
Load byte accumulator.
Oh, wait.
Right? Yeah, load byte.
Oh, yeah, we got to output the bash n.
Bash n.
Yeah, so load byte accumulator bash n addressing.
I.
Immediate is right. Store byte accumulator. Care out. Addressing. Direct. Yeah, we are. And I guess we don't need to branch, right? So now we're at end-if.
My question is, would
No. You always put the string constants at the bottom after the stop because they don't execute.
So
They can't. If you stick them in there, then the von Neumann cycle will try to execute them as instructions. Now that are you with me on that? Yeah. And in fact, if you do that, it will do that, and something will happen accordingly. Yeah. So end-if will be what?
add SP,
Yes. Add SP. Add how much?
2 minutes,
2 immediate. And what's our thing here? Pop what? Pound, what was it? Num? All right. Next. No, not dot end. Bzzzt. What do we need still? Yes. So, but what for the symbol? What was that? We still got some. Yes, we need message 1, MSG1, message 1. And what will this be? Oh, yes, but do I just put hi? Yeah, now it's dot ASCII. And now what? Quote. And now is it HIGH? Oh, you know what? We could have put the bash n here. I don't remember now how I did it in the program. I bet we put the bash n here. Well, let's just do this. Oh no, but what always has to come at the end? Bash x 0 0. And then what's next? Message 2. Yeah, and then what? And then dot end. But now, yeah, I see, now I don't remember what I did. Oh yeah, look, we did it the long way. Do you see how this is different in figure 6.8, the code? Now, did we do all of our logic correct? Or somebody check us out. Are we good? But now you see, we could just put the bash n in the ASCII string and not have to do that. We did it the hard way. But anyway, so this is better in the figure, in the text. Are we good? Okay, so here in figure 6.9 it shows how you write this in C, but then in assembler, in C you can indent and have the braces, and you know that it skips blah blah blah. But in an assembler, you actually have to branch around and then branch around the branch. You see how that works? How that's different? All right. Now, we're not going to take the time to go through these other ones in detail, but let's just take a look at how to translate a loop. Now watch this, you guys. First of all, what about letter? Is it a global or a local? This time it's a global, so now how's it going to be allocated? Fixed location memory with what? Dot block 2. Are you with me? Is everybody clear on that? So now we're back, we got to, okay. And now what do you suppose this in scanf letter so what will that be? That'll be how do we get a letter? Not deci, it's not a decimal, it's a letter. It's load byte accumulator from what? From char in. All right, and then store byte accumulator into letter using what addressing mode? Direct. Now, how do you suppose this while loop works? While letter is not equal to an asterisk. Yeah, so now in a while loop, where is the test? It's at the top. So what do you suppose? So here, let's do the while. Let's just do a few lines of the while. So it will be what? So it will be O. Yeah, there's a compare. Did I show you the compare byte instruction? I don't have a slide for the compare byte instruction. Yeah, okay, well. Okay, so in addition to a compare word instruction, there's also a compare byte instruction. Okay, so how will we do the test for the while? Well, first of all, how do we do the scanf? Let's do the scanf. That would be what? That would be load byte accumulator what? Char in, addressing, direct. And then how do we do it into C? Store byte accumulator into where? Letter, no, it's a global. No, D, right? Direct addressing. Are you with me? Is everybody clear? And now how will we do the test? While letter is not equal. Now let's do a non-optimize. From now on, sometimes we'll optimize, sometimes we don't. Let's do it a non-optimizing. Let's just, so what would we do? Load byte accumulator, what? Letter addressing. Letter D. And then what?
They need a symbol to branch back.
Yeah, we will need a symbol to branch back. Okay, so load byte accumulator, letter D, and then what? Compare byte accumulator what? CPBA. Compare byte accumulator what? What are we comparing it to? The asterisk constant. So quote, asterisk, quote, addressing? Immediate. That one immediate. Now, when do we want to do this? If here, it's while the letter is not equal to. So when do we want to branch around? When do we want to quit the loop? When it's equal to. So this would be what? BREQ to what? End while. Now does everybody see how that works? Let's see if we did it right. Oh, and then like you said, when we get to the bottom, what do we need to do? Branch back to the while. So do you see here on 002B, we branch back to the while, and we need the while up there at the top of that symbol at the top of the loop. Now, does everybody see how that works? So you study these examples, I think, and I think you can see how they work. So this is the while loop, yeah. And I'll see you on Monday.